Okay, so I'm gonna kind of mostly show you how to do state-based testing, but I just want to start with a kind of motivation a little bit, just to kind of ease into it about why it makes sense to do state-based testing more than just normal property testing. So I want to start with the simplest possible interface that I can think of, like a simple key value store. In this case here, I've got like an actual interface trait. It's like basically a get and a set kind of thing with strings. Just to kind of clarify, though, in some ways it doesn't have to be an interface. In theory, it could be like an actual. You could have get. You could easily just have the same thing here, where you had some concrete. You could actually have some concrete code, and that'll be fine. But I kind of find it easy to kind of think about these things often when it comes to interfaces. So like here's an interface I'm going to define and then test against that interface rather than the concrete stuff. But for the purposes of this, it doesn't actually make any difference. So we'll start with this KV2, and it has these two methods. Hopefully as simple as possible, just strings. There's no kind of new types or extra things. Let's kind of do what we would normally do in this kind of circumstance and actually write a property test for this thing. So we'll define our property test, and we'll define these two kind of, I'm just sort of coming up with some properties I want to think of. So for get set, I'm going to say generate me a key and generate me a value. I'm going to create a new k value store. We'll look into this later on, but basically I've defined an implementation of this thing which uses file systems on disk. So it actually has, like, for the key, it actually uses the file system path and writes to the file and stuff. And so there are most likely some bugs in here that we want to find, and let's see how well we can find them with property testing. So generate a key. I'm making a key just lowercase for now for potentially obvious reasons. We'll see in a second, but I'm going to generate a key that's all lowercase and generate a value, the value we don't really care about. Create me a key value store with some bugs in it. I'm going to try to put a value in. I'm going to get the value out, and then I'm going to sort of like a round trip to see that the value is actually the same. And when we run that test, we'll run that test as normal. This is a really good way to find if there's any actual bugs. If we were writing a value out, or we weren't actually writing the whole value out, or there were some encoding bugs, we would find those kind of things that we picked up with a round trip. So this would find some bugs with the actual kind of happy path. But then you go like, well, hang on, what happens if the key doesn't exist? So maybe we write a property to say, same thing, but let's just get a value that doesn't exist. But then maybe, hang on, what happens if we test where maybe we should generate a key, generate two keys, key 1, key 2, and then maybe we get, let's put the value into key 1 and try to get a key 2 kind of thing, filter. That kind of thing. Like, you can kind of imagine how many different ways are there to combine get and put. Like, do we put twice and get a different value? Do we put and delete? Like, the kind of combinations of these gets and puts kind of stacks up to an infinite number. And having to write these properties gets trickier and trickier. Maybe we need to insert a whole map. Like, I get to the point where I often generate a map of keys and values, put them all in, and then make sure when I get them all out there, they're there again. So the combination of these properties becomes kind of infinite. So I guess the question is, do we think that, even with those two tests, we didn't pick up, the obvious. I'll go back here. There are some bugs here that I've intentionally put, and we didn't find either of them with these two tests. How well do we think we're going to test these things before we find these bugs? And so as a kind of a extreme case, there's actually a thing called LevelDB written by Google, and there's a company that does state-based testing basically, and they get paid lots of money for that. And a really kind of funny example is that state-based testing found a bug where they generated a unique series of steps, of 17 steps to find the bug. So, you wouldn't think to actually do this in any kind of testing, unit testing, or even potentially like QA testing. But people would see this in the wild. But then when they ran it through state-based testing, it would randomly generate these different properties to find these bugs. So as a motivation, this is hopefully an idea that we can find bugs in systems that we're not otherwise going to find just by doing gets and sets, basically. So I want to kind of show you now what the actual interface looks like for state-based testing, because it's not as simple as it should be, or at least it's a little bit daunting to start with, but I want to kind of step through what that actually means. So we'll start with how it gets defined. So I'll just delete those tests now. Okay. To start with, this is kind of what you end up needing to do to get it working. So we'll start with, you kind of define that I want to do some sequential tests. Later on, we'll see how parallel fits into this. And we want to generate a series of these commands. We talk a lot about these commands. So I want to generate at least one command and up to 100 commands in sequence. We need to initialize our pure state for this thing, which we'll see more of in a second. But right now, state is just empty. There's nothing inside it. This is our model of the world. So we're going to model how we think this should work. It doesn't necessarily have to be the full thing, but we model something about this world, and we test against that. And it has to be pure. There's no immutable variables here. There's no I/O. It's just a pure memory data structure. And then we need to generate a list of commands, which we'll step through now. This is the bit that's the most daunting part of this thing. And finally, given that it's a state-based test, 9 times out of 10, there's going to be some sort of cleanup to happen. So in this case, I'm going to delete that file system recursively. So given temp directory, I'll make sure that there's nothing existing at the end of that. But maybe it's resetting I/O variables, maybe it's resetting the database. It doesn't really matter. It's just going to reset the world every time it runs to make sure that we have a clean slate. So obviously this might be quite slow. If we're talking against REST services or database systems, this might be quite slow to test. So the bit that's where things get a bit interesting is how do we think of these commands? So generally, as a rule of thumb, but obviously it's more complicated than this, you would imagine having one command per function you're testing. So we have get and put. So we would imagine we might have 2 commands that we want to test. So we're going to model what get's supposed to do, and we're going to model what put's supposed to do, and then we're just going to randomly generate those gets and puts in all sorts of different orders. So this is kind of a stub of what the bare minimum that you need. So I'm going to define a function that takes in our world, so this key value store. So this is the thing we defined, just so we can call it, we can talk to it. And we need to return a command IO where the command IO has to have a public state. So state being this thing, this is the model that we're testing. And this is a bit of trickery in Scala, but we're going to say this is the state that we need. And then you have to find 2 extra variables, which is like the thing that you're going to say, we're going to generate an input variable, and we'll talk through that in a second, and an output variable. Let's then step through each of these things for both get and set, and that might hopefully make sense. So I'm going to cut and paste that. So this is definitely a lot more prescriptive than you would otherwise see in property testing. There's a kind of like guide rails to guide you down the right path, and you'll see that there are benefits at the end of all this, but you need to kind of do all these things to get it working. So let's generate the put to start with, and you wire that into this this list of commands. Sorry, KB. And while we're there, let's also wire in the get. So now we've kind of wired those things up. Hopefully that will compile. But it doesn't actually do anything. So we're not generating anything yet, and we're not doing any kind of execution yet. So let's step through those. So let's talk about generating, which I think is probably the most obvious thing. The generating function in state-based testing is slightly different from the ones you normally see in property testing. So it's actually got an extra argument, which is this state. So you want to generate a new state based on the current state. So state in the beginning might be blank, but then over time you might build up some state. And so you want to generate state based on what the current world should be. So obviously with a key value store, the simplest thing I can think of is let's just have a map here. Now this is actually quite a good model in the sense that this should model the real world exactly. The state in some cases doesn't have to be the full world. You don't have to model every intricacy of the system, but you can model parts of the system. But in this case, we've got a full idea of what the key value store should look like. And so now I also need to modify my default state. So we'll initialize this thing with just an empty map. And then let's just do a generation. So the naive thing of generating, so I'll remove this one now. So this is our stub, we can get rid of the stub now. So generating a put, we need to generate something that's going to call the put function. What do we need to generate with put? If we look at the put function, we need 2 arguments. So what you often do in these cases is then we'll do a case class called put, which has the key and the value, and we'll do the same thing for get here. So we're just going to kind of almost turn those methods into data types. Notice that there's no return type here yet. That's obviously handled somewhere else. So we're just modeling the inputs to the function. Okay, so let's just do the naive thing to start with. For put, let's generate a key. What's it called? I've prepared one earlier, but actually let's just do gen string, gen lowercase maybe, range 1 to 10 for now. So let's just generate a string. Key and values are both the same, and we'll generate a put for key and value. Now this is slightly different from what you might expect. There's actually this option here. So this is what we want to generate, but there's actually this option wrapped around it. So you might imagine that there's a state in which we're trying to generate something that's impossible. Like we might have to call the database initialize function on our state before we can call blah. There's no point in some cases generating anything if the state is in a certain place. So for us, we always want to generate a put. even if it exists or not exists. So now I've kind of got some trickery here, which depending on whether you like it or not can kind of be a problem. There are these two type aliases on the actual command. So you can see that command has this state that has to be declared, but then input output is kind of then hidden away. There are reasons why I've done it this way, but basically input and output is specific to this command. The outside world shouldn't really need to know or care about what the input output is. It's just for this one command. Scala doesn't have any other way of doing it, unfortunately. So we need to declare what the input and output is for this. So this input here, this type alias, is going to be put. Now I'm lazy and I actually leave these things here. So this input here, this input here, this input here. I don't have to go and rename that if I change this, but you could in theory go and change put to here, to here, to here, to here if you wanted to. I find it easy not to have to do that because I can have to cut and paste it, or if I change it, I'd have to go and change 5 places, but that's a matter of style. Russell, I think, likes having the type there, but it's probably more readable having it there because then you can see this is put, this is put, this is put, this is put. Actually, let's just change it for now, just make it more readable. Okay, and the same here for output. So we'll talk about output here in a second. That should hopefully compile though. Okay, so we've generated a completely random key value every single time. We haven't looked at state yet. We'll come back to that in a second. And get in the same way. So let's just cut and paste that for get. We don't need a value. Put get in here and put get in here. That should compile in theory. But then also let's just do the nice thing and change these to gets as well, just to make it more readable. So far so good? Okay. So we'll just step through each of those functions one by one because there's kind of an order to how the functions you can think about them. So we're generating these things, we're doing some, so always generating them. But the question now is what are we actually doing? In fact, let's see what happens if I try to run that. Let's see what happens if I try to run that. I don't even know. It'll basically generate these commands, they'll be generating values, but then there's nothing to test, so we're not actually doing anything, so it's sort of obviously going to pass. Execute functions now, probably the most obvious one really, so we can then call, takes in this execute command takes in this environment, which we'll come back to at the end of this talk or towards the end of the talk, so just ignore environment. We have one of these puts has been generated, and we have to return either an error or the output. And the output in this case is just this unit at the moment. But you can imagine really the output is going to be this value here. So actually in this put case it is actually a unit, but in the get case it's going to be option of string. You'll see that one in a second. So let's just call key value dot put I dot key I dot value. Did I call it key value? Oh, sorry. Maybe we rename this to something useful. Okay. So that should hopefully compile as well. So the result of output has to be this unit. So let's now go and rename output to be unit because that's what we want. Get's obviously a bit more exciting in this case. So we can go key value.get I.key, and this output has to be option of string. So we'll just change that one, that one, that one, and output of get is going to be option of string. Hopefully should compile. So the execute is obviously where we're interacting with the real world, and in fact, not that it's necessarily relevant, but note that you don't have access to the state. The state sort of is available in all sorts of places that we'll see that are interesting, but in fact, we just want to model what does it mean to interact with the real world in a kind of isolated sense. So just talk to the real world and don't think about what the model is going to be. Just talk, like just do a get, just do a set, just do a talk to a database, do a REST call. And now I think if I call this, it should do it. And in fact, if we actually, if I put some print lines here on what the key values we're getting set, you'd actually see we're actually generating all sorts of gets and sets here. So something is actually happening. So now that we're calling a real world, obviously this may even pick up bugs. If we actually had errors, if we were generating completely random values and something was actually hitting a corner case, we would actually start to see errors bubble up and the test would start to fail if we were hitting some corner case where even what's basically fuzzing the interface, you would generate random values and blow things up. That would get you that far. But now we want to actually model what does it mean to do a get and a put. So the update function is basically where we actually just model that pure computation as opposed to the real world interaction. So state here has this map. So we're going to copy that over. Remember, there's no mutation here. So map equals s.map, and then we're putting. So let's dot key. We're going to append to that map the value that we think is the case. And so this is the old previous state, and this is the new state. So we would expect that to happen. Does that make sense? We're just modeling a put to a map. And for get, it's pretty simple. In fact, you don't do any modeling. There's no state change, so the S is just in and out basically. Then we just ignore this get value here. Ignore this var. This is the most complicated part of state-based testing. So let's come back to it at the end. So we just let's put that to the side to the last sort of example. And so now we're down to the final bit, which is really that kind of post condition. Like let's check the real world and check the model and see whether they line up. So environment again, we're going to ignore for now. But there's a state S0 and S1 or S basically. So S0 is the state before update's called, and then S is the state after that's called. So hypothetically, if you wanted to do a diff or check that the thing has changed, you can do that. In most cases, I don't use S0, but it has been useful for Russell when he's been doing it. So there are cases where it might make sense. But generally, if you have the state and you have the operation that ran, you could kind of almost recreate. You can always go back and forward with the state plus put or state plus put. You can always kind of recreate one or the other, assuming you think through that stuff. So for put, in fact, for now, we don't want to actually do any assertion. So the puts are always going to run and they're always successful. If there's any errors, we will know about them, but otherwise we actually want to say puts are always successful. It's only when we're actually doing a get do we want to say, does the world do what we think it does? So here we have the output of this output here from this execute is this thing here. And I would expect that if we did s.map.get on the key, I would imagine that equals, I think that's right. Yep, does that make sense? So this map of this world, of this pure key, let's see that it matches the output of the real world, if that makes sense. So we've done again, like some series of gets and puts on the real world and on the pure map in memory, the two should line up in theory. And we might call two puts and a get, we might call get with nothing. There will be some sequence of steps that we will do to get that function being tested and should, in theory, work.
Seems counterintuitive to me that the put, which is changing the state, is not the thing which you're validating that change of state has worked successfully, whereas the get, which doesn't change state, you are.
Yeah, it's kind of weird. I mean, you could, in theory, do the assertions, but the thing is, particularly when we come to parallel, you might see that there's uses like those execute functions in some ways should be thought of as atomic. So if you did like if you're doing in your execute a put and then to work out what the state is a get, that you want to kind of make sure you think of those things as atomic. What happens if the put happens and there's a delay and then the get happens? You want to kind of model that so you can kind of break them apart to see what the sequence of steps can be to get there. So you there are two types of modelings. You're modelling the sort of side effects, and then you're also modelling the kind of the kind of lookups or the kind of fetches as well. So there are kind of the side affecting ones and the non-side affecting ones, and you want to sort of see what happens if you run them in any order.
Just to follow that idea through, could you change ensure to actually compare the two states?
What do you mean? Sorry.
So like basically what it should be is like the original state up in put.
Yep.
So the original state should be that map plus an extra key, right?
You could do that, except that we're not. The purpose of this isn't to validate the in-memory state.
Yeah, this is sort
the
of
purpose of this is to validate. Like that's our internal model. The purpose of this is to validate that the real-world state is correct.
Because that will always be true. Like, assuming this code is always true. Like this, literally update and ensure basically get run together. So there's no world in which this update doesn't get called such that S0 plus S1 doesn't have that transition. You're not testing your own code. You're testing the other bit of code. If that makes sense. Like you can put the assertion in, but all you're doing is testing this line of code basically.
Yeah.
So you can add it if you want to for sanity checking, but that's not, as Russell said, that's not the purpose. The purpose is to make sure that the real world is doing the thing, not. And if you don't trust your model, then you're kind of got a different problem, I suppose.
What about the put ensure case? So if real world is database and that even putting can fail, right?
Yep. But then this is where the fail happens. So you turn that into an either left, and then that's a failure for the test.
Right.
Now, if you expect it to fail, if you actually expect the database insert to fail sometimes, then you can't return left.
Okay.
Your result might actually be an either itself. You might say database error is valid, and then you have to do the ensure to make sure that I expect this to fail in these cases. So when you return an error and execute, you're saying this is broken. This is not supposed to happen. I do not want to see this.
Right.
Basically.
Yeah, some cases that you actually expect some value, for example, like number of rows that update here.
Yeah, then you would return that.
Or ID.
Then you would return that. Yeah. So we could definitely return something here.
Okay.
Like we could say this could be hypothetically, this could actually be the previous value. That would actually be quite fun to add. You could say return what was previously there, and then you could definitely write ensure in that case. There is now a result from that interaction. So I'm keeping it simple, but absolutely you could definitely do that.
All right.
In fact, anytime you return a value here, you definitely want to put assertion in. So, well, sorry, you could put an assertion in. You can, the levels in which you can test these things are quite high, and you might just want to make sure that things don't blow up, or you might want to make sure that the gets always work. You might want to kind of add more and more validation and more modeling on top. Okay, so that should run, and it kind of passed. Why didn't that blow up? And not surprisingly, it probably blew up because this generator we did is not very good. It's just lowercase. So I'm just going to make it so easy to kind of keep changing this thing. I'm just going to change both these things to gen key, which should also be the same. But let's say hypothetically, because we know that file path, we're going to get in there and break some stuff intentionally. So I'm just going to cut and paste some code from before. So I'm going to generate a string that starts with one lower character and then can either be another lower character or a forward slash. So now that we know the file system's involved, chances are this might break. And in fact, let's give this a go. Okay, so it blows up. So that's actually, without having to think too hard about it, we basically got it to fail. And I do apologize in advance. Specifically, the scala-hedgehog implementation of the debugging is really shit. Like the logging I've done is really complicated, so really like very minimalist. So if you can't read this thing, you need to kind of understand that there are different parts of debugging that you need to be able to read. But the most important part of the state-based testing is the printing out of the sequence of things. So in this case, it generated two things. Ignoring this bar stuff, because we'll get to it later on. If you just imagine it's generated a put and it's generated another put. So it's generated a put where the key was a/a and the value doesn't matter. And then it generated a put with another a. So given that it created a directory with an a in it, you obviously then can't create a file called a. So it's already kind of found the absolute bare case. And notice, interestingly enough, that there's a's everywhere. If I were to hypothetically go and say no shrinking, let's run that again without any shrinking. So this is the magic of property testing in general. Like there's an error. Where is it? I have to go and think about it now. I have to go and kind of recreate it. Like back when I was at Ambiata, I used to actually cut and paste this kind of thing, run the test in manually, and then start deleting it and modifying and changing so I could actually work out what the bug was. The beauty of shrinking is when it works, we'll run that again and you'll see just the absolute, ideally like A's and blanks and just the absolute bare. Here we go. Here's another case that's failing. If I put an A and then I get an A with a slash, I actually get back a value when I don't expect it. So the keys when they contain slashes mean different things to the file system-based version. Okay, so that's not great. So let's I'm going to cut and paste another implementation that fixes this thing. So here's basically the same thing. Where in this case the path that I'm using actually then neural encodes it. So there's no directory structure anymore. I'm just going to have like a file name, and the file name will be like it contains slashes. The slashes get percentages and stuff basically. So I'm going to run that again where not that one but this one. This in theory should work. It did for the testing I did earlier. So now we've generated 100 examples where it's going to get put with slashes and lower cases and stuff, and that's worked. Although in fact, I wonder what would happen if I let's be cheeky. I actually haven't tested this before, so I've got no idea what's going to happen. Let's generate a string of just Unicode. Let's give it a real workout. Okay, and make sure like you can't generate a key of 0 values. That's probably going to fail anyway. But let's give this a go. Unicode characters. Let's see what happens. Okay, so our Unicode escaping actually works. So that's good. Okay, so that's already amazing, I reckon. Like already, I'm quite lazy, and I actually find this model of testing actually better because I get really like I put my test in saying here's a map of keys, and then I get one of the values out and it works, and I kind of leave it at that. This is just I find this easier. Like you put a little bit extra effort in the beginning, and now I never have to think about modeling the interactions between get and put ever again. And even though you put more work in each one, you don't have to model different combinations of things. Imagine adding delete, imagine adding all sorts of other listings. Every time you add one of those things, you only have to add one of those commands, and then you get the testing for free, basically. Okay, so that's pretty good, but what do we think this would work in parallel? So this is obviously just going to generate these commands in sequence. This is where shit gets really, really cool. There's a slightly different way of testing parallel code. You just need a few extra things. KB2. So the only difference is that there are now two ranges. So in the beginning, for sequential ones, you're just saying how many commands in sequence. In parallel, there's two phases, and I'll show it failing to kind of give you a better visual sense of this thing. But basically, with parallel test, you generate a sequence of initial steps in sequence to make sure that you're kind of setting up your database, like some inserts, just to get things going. And then you then fork two threads in Java and run those in parallel. So how many of those do you want compared to how many of the setup do you want? So here we'll generate 0 to 10 steps to start with, and then we'll generate 1 to 10 forked number of processes or commands.
But the key thing is there's only ever two things running.
Yeah.
In parallel.
Yeah, this isn't like run 10 threads, it'll literally only run 2 threads. So if you read the paper from John Hughes, he kind of points out, I don't know how much he proves it, but he basically makes the assertion or kind of makes the claim that he thinks that any bug that involves concurrency, obviously is hard or easy to hit with more threads, but you can boil it down to anything that requires 2 processes basically. So it's much easier to debug the code if you can just see these 2 commands run in sequence rather than these run in 100 threads. You can kind of just boil it down to a series of 2 threads. So in practice, it seems to find all sorts of bugs in parallel. So we're going to reuse the same commands. Nothing changes the commands. Nothing changes for the cleanup. And the only other difference is this probably won't compile now because we need to sort of say where's the. Oh, sorry. The only other difference is we need to say how many threads we want to run or which thread pool do we want to use. So you'll complain about saying missing execution context. So depending on which one you want to use, I'm being really lazy and I'm just using the Scala's default one. So let's just put that up here. So you can either import that or make your own or whatever. You just need an execution context in scope. So let's just change this now to parallel. And we're just using this one here with lowercase values and slashes. Do we think this is going to work? Do we think our code is actually parallel friendly? And this is where things get harder to test. Why didn't that find it? Interesting. Maybe I need to put a thread.sleep in there to really crank it out. So, come on, bullshit. Bullshit.
Is it all using parallel?
Yeah, it should. Been made a fool of.
The file sequential is still the same.
Which one? Sorry.
So
this thing here. Yeah. Okay. That's that file when I wrote last time. That's interesting. I don't know. That's why that's not working.
You have your own example in Hedgehog, right?
Yeah. I'm just running that one again. Sorry guys, that's a bit annoying. I could have sworn this was failing last time. Okay.
Oh. Okay. Yeah.
Weird. That's really weird. Okay, well, this is the same code, so I just want to show you what it looks like when it fails more than it matters what the code's doing. But so this is where I apologize. The scala-hedgehog debugging is really annoying, but all the information you need is there, but it's just a bit hard to read. But the really critical part is the sequence of steps. So ignoring everything below, like once you sort of stop seeing bars, you're at the end of it. But it's this bit here basically. So there are 3 parts to it. So prefix is the bit that happens in series on a single thread. So to initialize the database, to get some puts in, it runs one put and puts A with a capital A value, and then creates 2 Java threads. And on one thread runs get, and on one thread runs put, and then unfortunately this is where debugging gets hard to read. But basically it says when I expected to do a get. I read black blank, but I expected to get this A back, for example. So this get, and if you go back and run through it in your head, you can imagine if I did a get where put happened and then get happened, I would expect to see a capital A.
This doesn't make sense to me because it's put happened in prefix in the.
That does make sense because the bug is that there's actually a new file being created with its blank. So the bug is the bug is happening basically. Well, yeah, the bug is basically the file write is open, the contents is now blank, and then while this has happened on the other thread, someone's done the read at the same time that someone's done the file write open at the same time. So this is not atomic. This sort of file, this crappy Java IO code that I've written is not atomic, and so therefore this get can observe incorrectly the state of this put. So again. And I would claim there's absolutely no way your unit testing will pick this up. It's not going to happen. You will find this in production first. So this is where state-based testing really like just nails it. Now, obviously, it doesn't pick up everything. It's more complicated than that. But for things that are really just dumb stuff like this, you will ideally find. Okay, so what I've done in this case, this code is all basically the same. I'll then run this version, where if you look in the file parallel version, what I'm doing here is I'm creating a temporary file with some unique name. I write that file out, and then I do an atomic rename at the file system level. So I would expect this never to fail. Yep. So this is pretty dumb code, but you can kind of see that if there are sort of dumb, obvious bugs, you might find it. Although I don't quite know why this one's not failing. Anyway, we'll go back to it. So does that make sense? I might go back to that error message quickly. It is unfortunately hard to read, and my advice is, and actually Russell probably is better at reading this now than I would be, but my advice is I kind of get a sense of what's happening here, but unfortunately what happens is I print out all the failure cases. So what property testing does in Hedgehog specifically is it runs in parallel. It will run the get and the put in parallel with two threads. It doesn't even try to work out whether they ran just before or just after each other, what times they were running. It literally just runs them blindly, and then it collects the results. And then it does a thing where it tries to take the prefix code, the prefix state, and then run that through, every single possible combination. So if you generated, I can show you the whiteboard just quickly. Sorry, Kev, just sorry about it too much. If you can imagine if you ran X, Y, Z on, there's an A, B, C setup, and then M, N, O. What Hedgehog is going to do is it's going to say, it can't tell, this is on thread 1 and thread 2, it can't see what happened, it can't see that this actually, it doesn't try to kind of work out the time where these actually ran in sort of overlap. So what it does is, it collects the outputs from here, and it collects the outputs from here once, it runs the commands once, and then it will try to linearize. So it will try to do this, and then it will try to do this. It will literally run through every single possible combination of both sides to see whether those ensure functions then are correct. So ensure is actually going to get called for every possible combination of these things. So you can imagine with our simple case, we had, our put one, and we had a get and a put. It will try to run that, and then it will try to run that. And if the ensures don't work on both sides, something's wrong. So you in fact, I guess in theory you could find a bug where it linearizes something and says everything's okay, but in fact that's not actually what happened. But in theory, often you'll find a bug where you can't. This state can't possibly have happened. You're finding a state here that there's no possible way to get to the point where this ensure didn't happen the way that it did, as you can see in the bug that it just found. So that's why debugging is so hard to read. It's because what do you want to see printed out? So here you're kind of seeing printed out, this is one of the sides, and this is the other side of the linearization. If you can imagine if you had 20 commands there, you would see the printing out of 20 different possible combinations of this linearization. So it would just get really, really messy. So that's why I recommend getting a sense of what happened. And that's what I'm saying here, no valid interleaving, which means I could not find a case where this made sense. This is the thing you want to focus on. You want to focus on, try to work out why, almost run it manually at this point, try to kind of work out why, if I did two puts or a put and a get, why those two things wouldn't work out. So you can spend a long time staring at this output and working out what actually happened. So this is, if you actually ever get a bug, I suspect Russell probably spent a fair bit of time trying to work out what it really meant. Yeah. So once it finds a bug, you can spend a long time just going, what the fuck does that mean?
To me, the only trouble I really had with it was when shrinking was involved.
Yeah.
That made it harder. I had to turn shrinking off to reason about it.
Let's run that again. But it's kind of a double-edged sword. So let's just do some more. You might imagine all sorts of. Yeah. So here we go. So now we're kind of getting more complicated cases, but where the pure bug might be simpler than that, but. Yeah, so you can turn it on and off and see what happens. And again, I would try to reason about it as much as possible, but obviously some debugging and some print statements probably necessary at some point.
Sure. The other thing I had a question about was where, with that test failure, with shrinking enabled, it still had that prefix, but that, as in it had that put.
Yeah.
That's not needed, is it?
Probably not. Depends on whether you had a 0 or 1 here. It's not shrinking, particularly with state-based testing. I suspect, my intuition is it's never going to find the perfect shrink anyway. You can only do so much. So yeah, okay. You'll find it, as you saw, you ran it a few times and you got a different shrink every time. Particularly with parallel tests, all bets are off in terms of reproducibility anyway. So
yeah, it was just that, as in you could have shrunk that away.
Yeah. And if you keep running it, you might find eventually it would actually print that out. So. Okay, does that make sense? Does anyone have any questions on that before we go on? That's the easy case, or not easy case. That's the happy path, as it were. Like there's no vars involved, but we'll kind of now. I want to try to change things now to kind of make it a bit more fun, if that makes sense. Cool. Okay. So I don't know whether I should change that or cut and paste the whole thing. Maybe I might just add it quickly. Okay, so I'm going to change the slide to kind of show why vars are there, because vars where things get a bit, they're not hard, they're just not intuitive, basically. So let's say, for example, we just basically have a simple put for something, and rather than getting it with the key, I want to get with the ID. So think of int as an ID here. I don't know if we want to rename it or not. I can kind of, if it makes it easier, I can kind of do that. But I'm generating a database ID now, so now we're kind of getting much more kind of cruddy. So like adding something to the database, getting an ID back, and only get it back through the ID. So now there's an interaction where you have to see the output of one to then do something else with the input. Before, like you can't randomly generate one of these IDs. You're gonna have to know what it is specifically to do something useful. So let's go through this. So put, for example, now this is no longer a unit. It's going to be an int. This is why I like that output input stuff, because I've got to change all this stuff. Let's see what it doesn't before it doesn't compile now. Okay, so now we can see get. So sorry, I'm trying to do a get with this key. Okay, so this is where things get. This is where we have to kind of think through this stuff. Now we're trying to do a get on something we don't know. We have to base it on the output of the execution. So the first thing you're going to have to do is in this put command. Notice in update for put, you get access to this var. So if we go and look in var, I don't want to get too bogged down, but this is kind of like it's like a stub. It's like an abstract holder for what we think is going to happen. So it's not actually the variable. It's going to be a unique point of the way to get that thing. So it's hard to explain why it's done this way, but basically the idea is you generate the commands before you've actually got the outputs. So you generate a sequence of commands and you know that the output of X is actually going to be Y, and it's going to be Z, even though you don't know what the values themselves are until the end, if that makes sense. So you've got a holder for these names, but you don't actually have the values. So this var is not the real variable. It's just like it's literally a unique number to say when I eventually run with this environment, I can look it up. And you'll see how the lookup looks in a second. But so now what we want to do is we actually want to install over here. So this map is no longer string to string. It's going to be a var string to string, basically. In fact, it might be safer. To do this. I'm not sure. I don't know whether. Oh, let's see what happens.
It's not bar ID.
Not sure whether this has the right hash code and stuff. We'll find out, I guess. So we're going to have. So rather than this being an actual string, it's going to be a lookup to a string at some point, and you'll see you'll see the implications of this in a second. So let's see what doesn't break. Let's see what breaks. I haven't actually done this before, so this might take a bit longer than you might expect. Oh yeah, sorry. Yeah, sorry. That's what you were saying, wasn't it? Okay, sorry. Var int. Yep. Right. Yep. Does that make sense? So we don't actually have an int. We have a lookup to an int at some point. So it's like a stub or something like a non-concrete value. Okay, so now we're in get. The key here is okay. So now we've generated random keys to do this stuff. That's not quite what we want to do. What we want to do is generate random IDs from that map. So this is where this gets a bit more interesting. So we have this state now. So we're trying to generate a get based on the previous state. So rather than doing random keys and hope that they line up, let's go the map. Let's go to list. Just go map. Oh, actually, sorry, that's pattern match on this one. Okay, so if we don't have any keys, if get has been called the first time, then let's return none. So this is what this is here for. There's literally nothing useful we can do. Or, I mean, yeah, there's literally nothing useful we can do here. We can't call get unless we actually have a database ID. And so obviously we know this is going to be a, head and tail. And then let's generate gen dot, is it the element? No, it's choice.
So it's not some. So it should be nil instead of none.
Oh yeah, that's released. So.
No. Sorry,
yeah,
you mean here. Sorry, you're right. Yeah. So nil. So the empty list returns none. Otherwise, we have here. We're going to call this element. So basically pick one of these things. Actually, what we can do is probably keys. we don't actually care about the variables here. Okay, does that make sense? So we're going to, of all these keys, we're just going to pick one of them basically. So we know this has already happened. Again, we don't even need to know what the values are. We're just going to pick one of these things randomly. So now we're getting somewhere better. Oh yeah, get, sorry. And we're going to change get to be the same thing here, var int. Okay, what's going on now? Oh, get, sorry. Over that, so get's going to take one of these vars. So I'm going to pick one of these ints and then I'm going to map it with over with get. Sorry. Yeah. Does that make sense so far?
Yep.
So picking, so now from this state we're picking something that we know to be true. Like there'll be a put before in the sequence of steps. There'll be a put, and so once there's a put, that will get returned with an actual variable that we can then use to look up an actual value with this database ID. It'll hopefully make